All right, let's dive into something I think you're really going to find interesting: empirical software engineering.
Yeah, it's a pretty hot topic.
We've got these excerpts from a handbook.
Oh, cool.
All about teaching it. And it's really about how we use data to make better decisions in software.
It's about bringing that real-world practicality to the research.
Yeah.
And we're going to be exploring what it is, how it's studied, and why it matters, whether you're knee-deep in code every day or just curious about software.
No more just assuming things work.
Right.
We're going to look at the proof.
Yeah.
But first, what exactly is empirical software engineering? It sounds kind of intimidating.
It's actually more straightforward than it sounds.
Okay.
Think about trying to improve a recipe.
Okay.
You wouldn't just add ingredients randomly, right?
Right.
You'd experiment, measure what happens, and then adjust based on what you learn.
Okay.
And that's the heart of empirical software engineering.
I like that.
Using data and evidence to understand what works, what doesn't, and why.
Okay, so it's like baking, but for code.
Mm-hmm.
You're not just throwing lines of code and hoping something sticks.
Yeah.
You're being deliberate, gathering data, and making informed choices.
Exactly. And one of the core concepts is this idea of the pragmatic cycle.
Oh, okay.
And it's this idea of constantly iterating.
Okay.
Going from a problem to a theory about why it's happening to testing that theory and then using the results to refine your approach.
So it's kind of like a feedback loop where you're constantly learning and improving.
Precisely. Now, think about the kind of questions that empirical software engineering tries to answer.
Okay.
One big one is about existence.
Existence, okay.
Like, does continuous integration actually happen in smaller development teams?
Right.
We might assume so, but we need data to confirm it.
Right. You know what they say about assuming? Sometimes what seems obvious isn't true in practice.
Yeah.
Data can really bust those myths.
Exactly.
What other kinds of questions are we talking about here?
Well, there's also description and classification.
Okay.
Let's say teams are struggling to adopt agile.
Right.
What are the common roadblocks they hit? Can we categorize those challenges and find solutions? That's where description and classification come in.
So it's about going beyond just saying, it's hard.
Yeah.
And actually pinpointing the issues. Okay, that makes sense. Is there a way to actually compare different approaches using this?
Sure.
Like, how do I know if technique A is better than technique B?
You're thinking about descriptive comparative research.
Okay.
This is where things get interesting. Like, imagine trying to decide between test-driven development and a more traditional approach. Does one actually lead to higher code quality?
Okay, now that's hitting closer to home.
Right.
In my own work, we're always debating what's the best way to do things.
Exactly.
You're saying we can actually use data to see which techniques truly deliver.
Yeah.
Mind blown.
And this is one of the big things that I think is missing in a lot of software engineering research is that they don't go beyond just describing what they observe.
Oh.
Like, what you really want to do is develop theory.
Wait, so theory isn't just some abstract thing academics love?
Yeah.
It actually has practical implications.
Yes, absolutely.
Okay.
A good theory acts as a roadmap.
Okay.
It connects the dots between what you're observing and helps you apply research to your work.
That makes sense.
Like, think of it this way. If you're trying to navigate a new city, would you rather have a map or just a list of individual landmarks?
Yeah, I'd want the map.
Right. The map gives you the context.
Totally.
For how those landmarks relate to each other, just like a good theory helps make sense of all the data.
So we've got the what and the why of empirical software engineering. But how do people actually learn this stuff? I mean, getting people excited about rigorous measurement and data analysis.
It definitely has its challenges.
Yeah.
One of the biggest hurdles is getting people to understand how crucial it is to measure the right things.
Right.
The dependent variables.
Okay, so spill a tea. Can you give me an example of where choosing the wrong thing to measure can really mess things up?
Let's say you're evaluating a new bug finding tool.
Okay.
You could just measure how many bugs it finds.
Okay.
That's recall.
Yeah.
But would that be enough?
That's a good point. I mean, finding a bunch of bugs is great, but what if they're all super minor or easy to fix? That doesn't mean the software is better overall.
You're getting it.
Okay.
So instead of just focusing on bug count, maybe you measure the time developers spend fixing those bugs.
Right.
Or how those fixes actually contribute to the project's success.
Okay.
Choosing the right dependent variable, make sure you're measuring what matters.
This is making me rethink how we track success in my own team.
See, that's the power of this stuff. It could really make you evaluate your own practices
Totally.
and make better decisions.
All right, so Besides choosing what to measure, what else is important in teaching this? What's the secret sauce?
Another key ingredient is introducing students to different philosophical perspectives on research.
Uh-oh. That sounds a bit heavy.
Not as existential as it sounds.
Okay.
Things like positivism, falsificationism, and realism.
Good.
Understanding these perspectives helps students understand how studies are designed.
Okay.
And how they're interpreted.
Okay, so it's like having different tools for different jobs.
Exactly.
You wouldn't use a hammer to screw in a light bulb.
Right. Each philosophical perspective offers a different way of approaching research, and understanding those differences can help you choose the right one for the job.
Makes sense. Now, I have a feeling all this ties into another concept you mentioned earlier, construct validity.
Right.
Remind me about that one.
So remember we talked about measuring things that are hard to pin down, like software quality, developer productivity.
Right.
Construct validity is all about making sure you're actually measuring those abstract concepts.
Okay.
In a way that makes sense.
Okay, so it's not just about counting lines of code or bugs fixed.
Yeah.
It's about finding ways to capture those fuzzier, super important aspects of software.
Exactly. You have to operationalize those concepts, define them in a way that allows for measurement, and that often means developing these sophisticated statistical models that take into account multiple factors.
This is giving me a whole new appreciation for the complexity of software engineering research.
Yeah.
So how do researchers actually analyze all this data they're collecting? Do they have any special tools or techniques?
They use a variety of methods.
Okay.
Qualitative and quantitative, depending on what they're trying to understand.
Okay. Break those down for me. Qualitative versus quantitative.
Okay, so think about it this way. Qualitative methods are like being a detective.
Okay.
Looking for clues and patterns in things like interview transcripts or observations to understand the why behind something.
So kind of digging into the human side of software.
Exactly.
Understanding motivations, experiences, and perspectives.
Exactly. And a common one is thematic analysis.
Okay.
Where you identify recurring themes or patterns in the data.
Gotcha.
Quantitative is more about crunching the numbers.
Right, so that's where stats come in.
Exactly. Testing hypotheses and drawing conclusions based on data.
So it's like using the right tool for the job.
Mm-hmm.
Sometimes you need that magnifying glass.
Yeah.
Sometimes you need a calculator.
And sometimes you need both.
Right.
Right. Combining qualitative and quantitative methods can give you an even richer understanding.
That makes total sense. You get the big picture from the numbers and then the nuances from the human stories.
Exactly. And one technique that we haven't talked about yet that I find really interesting is mining software repositories.
MSR.
Or MSR.
Okay, this sounds like archaeology for software.
It really is. Imagine being able to go back in time and see how a software project evolved from its very first line of code.
Whoa, really?
Yeah, with MSR, you can do that. You can dig through all this data stored in repositories like code changes, commit messages, bug reports, even online discussions.
Hold on, so you can actually analyze all that information to understand how software changes over time.
Yes.
How developers work together, and maybe even predict potential issues before they arise.
Exactly. It's like having a window into the entire life cycle of a project.
Okay, that's incredible.
We can use this data to answer all sorts of questions.
Okay.
Like, how does the code base change in response to bug reports? Or how do different development practices impact code quality and defects?
This is blowing my mind. It's not just looking at the code itself.
Right.
You're looking at the whole ecosystem around it.
Exactly. It gives you a holistic view of software development.
Yeah.
Revealing the social and technical dynamics that shape the final product.
Okay, before we get too lost in the wonders of MSR, I gotta ask, are there any ethical concerns with digging through all this data, especially if it involves information about individual developers and their work?
Yeah, data privacy is absolutely paramount when it comes to MSR.
Right.
It's essential to respect the privacy of developers and protect their identities, especially when dealing with potentially sensitive information.
So things like anonymizing the data, getting consent, and being transparent about how the data will be used are crucial.
Absolutely.
Yeah.
We want to make sure that MSR is being used responsibly and ethically and not creating a big brother situation where developers feel like they're constantly being watched.
That makes sense.
So we want to be very careful about that.
Okay, so once you've mined all this data, how do you make sense of it? I'm guessing it's not just staring at spreadsheets for hours on end.
No, you're right.
I mean, how do you make it understandable?
That's where data visualization and descriptive metrics come in.
Okay.
Think of them as your storytelling tools.
Okay.
They help turn that raw data into something that's easy to understand and communicate.
Okay. I love a good story. So data visualization, that's where all the cool charts and graphs come in.
Exactly.
The ones that help you see patterns that might not be obvious just from looking at numbers.
Exactly. A good visualization can reveal insights that would be lost in a sea of numbers.
And what about descriptive metrics?
Yep.
Are those like, averages, percentages that give you kind of a quick snapshot of the data?
Exactly. They provide a concise summary of the data, allowing you to quickly grasp key characteristics without getting bogged down in the details.
This is making me realize how much data is out there.
Yeah.
Just waiting to be explored, analyzed. It's like a gold mine of insights.
It really is, and we've only scratched the surface.
Wow.
There's a whole world of empirical software engineering techniques waiting to be uncovered.
Okay.
And one that we haven't talked about yet is simulation.
Simulation. Okay, help me out here. Is this like creating a virtual model of a software system?
Yes.
To test different scenarios? Like a digital playground for software engineers.
Exactly. Simulation allows us to create a controlled environment where we can experiment with different variables and see how they impact the behavior of a software system.
So instead of building and testing software in the real world, which can be time-consuming and expensive, you can just run simulations to try out different approaches and see what happens.
Exactly. It's a safe and efficient way to explore different design choices, to test the limits of a system, and to even predict potential problems before they occur in the real world.
Okay, that's seriously cool. What kind of things can you simulate in software engineering?
All sorts of things. We can simulate things like the spread of defects in a code base. We can simulate the performance of different software architectures.
Wow.
Or the impact of changing team dynamics on a project's success.
So you can basically create these virtual worlds where you can tinker with different variables and see how they affect the outcome of a project.
Exactly. And it's becoming increasingly important.
Yeah.
In software engineering, as the systems we build become more complex and interconnected.
This is all making so much sense now.
Good.
But I have to ask, how do you actually create a simulation that accurately reflects the real world? I mean, it seems like there's a lot of potential for things to go wrong if your assumptions are off.
You're right. Creating a valid and reliable simulation is a complex task.
Right.
That requires a deep understanding of the system that you're trying to model.
Okay.
You need to carefully consider the factors that influence its behavior.
Yeah.
Choose the right level of detail. And make sure that your assumptions are grounded in reality.
So it's not just about plugging numbers into a computer program.
Right.
It's about blending technical expertise with a deep understanding of the real-world context.
Precisely. It's about finding that sweet spot where your simulation is complex enough to capture those essential dynamics of the system, but simple enough to be manageable and interpretable.
All right. I think I'm starting to get a handle on this simulation thing. But before we move on, I want to go back to something we talked about earlier, action research.
Okay.
It sounds like a really interesting approach.
Yeah.
But I'm still a little fuzzy on how it actually works.
Okay, so action research is all about bringing researchers and practitioners together to solve real-world problems.
Okay.
It's a collaborative approach where everyone is involved.
Okay.
In the process from identifying the problem to developing and testing solutions.
So it's not just researchers observing from a distance. They're actually getting their hands dirty working alongside the practitioners.
Yeah, exactly. And that's what makes it so powerful.
Okay.
You get the best of both worlds. You get that theoretical rigor of academic research. Combined with the practical experience and insights of the people who are actually facing the problem.
Okay, I can see how that would lead to more relevant and impactful research findings.
Exactly.
So walk me through the steps involved in action research.
Right.
What's the typical process?
It usually follows a cyclical pattern of planning, action, observation, and reflection.
Okay.
You start by planning what actions you're going to take.
Okay.
And you implement those actions. You observe what happens.
Okay.
And finally, you reflect on the results.
Right.
And you use those insights to inform the next cycle of planning.
So it's a continuous loop of learning and improvement with everyone involved in the process.
Right. And that iterative approach is what makes action research so effective, because you're constantly refining your understanding of the problem.
Right.
And adjusting your approach based on what you learn.
Yeah, I know. All right, I'm sold. Action research sounds like a win-win.
It is.
For both researchers and practitioners.
Yeah.
But I imagine there are also some challenges involved, right? Like, how do you manage expectations and ensure that everyone is on the same page?
Yeah, collaboration is not always easy.
Right.
One challenge is finding that right balance between the needs of the research and the needs of the organization.
Okay.
You don't want the research to become too disruptive to the organization's day-to-day operations.
Makes sense. So it's all about communication, collaboration, making sure everyone understands the goals of the research, how it's going to benefit the organization in the long run.
Exactly. And it's important to be transparent about the process.
Right.
And involve stakeholders from the beginning to ensure buy-in and support.
This has been an amazing overview of action research.
Great.
Now, before we wrap up this section, I want to touch on something we haven't really discussed yet, the role of philosophy in software engineering research.
Okay.
I mean, philosophy seems like a completely different world than code and data.
It might seem that way, but it's very relevant.
Really?
Yeah, understanding different philosophical perspectives can actually be really helpful in guiding how we approach research.
Okay, I'm intrigued, but can you break that down for me? What are some of the philosophical perspectives that are relevant to this field?
One important one is positivism, which emphasizes objective observation and measurement.
Yeah.
It's all about trying to uncover universal laws and principles that govern the behavior of software systems.
Oh, wow. So it's like the scientific method applied to software engineering?
Exactly. It's about trying to find those fundamental truths that apply to all software, regardless of the context.
So are there universal laws of coding?
Well, that's what the positivists believe.
Wow. Okay, but what about the human side of software development? How do we account for the fact that software is created by people, used by people, and it's embedded in all this social context?
Well, that's where interpretivism comes in.
Okay.
It recognizes that software isn't just a technical artifact, but it's also a social construct that's shaped by human values and beliefs and practices.
So instead of just looking at the code, we're also considering the human factors.
Yeah.
Like how developers collaborate, how users interact with the software, how cultural norms influence design choices.
Yeah, exactly.
Okay, that makes a lot of sense. But what if we want to bridge the gap between these two perspectives, between that objective world of code and the subjective world of human experience?
Well, that's where critical realism comes in.
Okay.
Which tries to find a middle ground between positivism and interpretivism.
Right.
And it acknowledges that there are objective realities out there.
Yeah.
But our understanding of them is always shaped by our social and cultural context.
So it's about being aware of our own biases and assumptions when we're doing research and recognizing that there are multiple ways of interpreting the same data.
Exactly. And all of these different philosophical perspectives can influence everything from the research questions we ask to the methods we use to collect and analyze data.
This is making me realize that philosophy isn't just some airy-fairy academic subject.
No, it's not.
It can actually have a real impact on how we approach software engineering research.
Right.
And even how we design and build software.
Absolutely. And I think it's especially important in a field like software engineering, which is constantly evolving and grappling with complex social and technical challenges.
Okay, I'm starting to see the light. Philosophy isn't about replacing code and data.
Right.
It's about providing a framework for thinking critically about how we use them.
Exactly. And that critical thinking is what allows us to push the boundaries of knowledge and to create better software for everyone.
This has been an amazing deep dive into the foundations of empirical software engineering.
Good.
I feel like I have a much better grasp of the different philosophies, the research approaches, even the ethical considerations involved.
Good.
I'm ready to keep digging, but for now, let's take a break and we'll come back and discuss a specific case study that showcases the power of empirical software engineering in action.
Sounds good.
Ooh.
All right, are you ready to see this stuff in action?
Let's do it.
Let's talk about a really cool research environment called the Green Lab at Eindhoven University of Technology.
The Green Lab. What is this? Some kind of eco-friendly coding space with plants and solar panels?
Well, it's definitely focused on sustainability, but not quite in the way you're imagining. The Green Lab is dedicated to studying energy efficiency in software.
Oh, wow.
They're using these empirical methods to figure out how to make software more environmentally friendly.
Whoa, hold on. I never even considered that software could have an environmental impact.
Yeah.
How does that even work?
Think about all the energy it takes to power the servers that run our websites and apps and online services.
Okay.
And then add in all the energy used by our devices to access all that software.
Right.
It adds up quickly.
Yeah, that's a good point. So the Green Lab is basically trying to reduce the carbon footprint of software.
Exactly. They're conducting experiments in this controlled lab environment where they can measure the energy consumption of different software applications and hardware configurations.
Wow.
They're looking at how different programming languages, algorithms, even user interface designs can impact energy usage.
So they're basically like software detectives tracking down the energy hogs and figuring out how to make them more efficient.
Yeah, that's a great way to put it.
I like that.
And they're not just identifying the problems.
Yeah.
They're also developing tools and techniques that can help developers create more energy efficient software from the ground up.
This is seriously impressive stuff.
It is.
What kind of experiments are they running in this Green Lab? Give me some juicy details.
Okay, well, one study they did focused on the energy consumption of ads and analytics in mobile web apps.
Okay.
And they found that those pesky ads can actually drain your battery life significantly.
Wait, really? I always knew those ads were annoying, but I had no idea they were such energy vampires.
It's true. They measured the impact and found that they consume a surprising amount of energy, especially on mobile devices.
Okay, that's both fascinating and slightly terrifying. So is there anything we can do about it?
Absolutely. That's the whole point of this research.
Right.
By understanding how these different components contribute to energy consumption,
Right.
we can start to make better choices.
Right.
For example, maybe we need to design more energy-efficient ads or encourage browser vendors to implement features that limit the impact of ads on battery life.
Okay, that makes sense. So it's not just about blaming the ads, it's about finding solutions.
Right.
That balance functionality with sustainability.
Exactly. And they've also done some interesting work on autonomous driving robots,
Okay.
exploring how different offloading strategies affect energy consumption.
Hold on. Offloading strategies. Can you bring that down for me?
Sure. So it's about deciding which tasks should be performed on the robot itself versus being offloaded to a more powerful server in the cloud.
So it's like finding that optimal balance between local processing and cloud computing, kind of like deciding whether to do your laundry at home or send it out to a laundromat.
That's a great analogy.
Thanks.
And their research found that this choice of offloading strategy can have a big impact on both energy consumption and performance.
Okay, so this research could actually help to design more efficient autonomous systems, which is super important as we see more and more robots and drones being used in all sorts of industries.
Exactly.
We definitely don't want a fleet of energy-guzzling robots running around.
We do not, and beyond these specific studies, the Green Lab is also contributing to the field of empirical software engineering by developing new tools and techniques for measuring energy consumption, and they're teaching these concepts to students.
So they're not just doing the research, they're training the next generation of energy-conscious software engineers.
Exactly. They're creating a hub for energy-efficient software research and education, and they're collaborating with industry partners to apply these findings to real-world projects.
This Green Lab is seriously blowing my mind.
I know, it's pretty cool.
It's amazing to see how this kind of research is being used to tackle such an important issue.
Yeah, it highlights the power of this approach to address real-world challenges and to drive innovation. But before we get too carried away with the Green Lab, I want to zoom out a little bit and go back to something that we talked about earlier, which is measurement.
Measurement, yeah, we touched on it briefly before, but I have a feeling there's a lot more to unpack here.
There is.
I mean, measuring lines of code seems pretty straightforward.
Yeah.
But what about those more abstract concepts like software quality or user satisfaction? How do you even begin to measure those things?
You're right. Those are much trickier to pin down.
Yeah.
And that's where this idea of construct validity comes in.
Okay.
Which is all about ensuring that you're actually measuring what you intend to measure.
Okay.
Especially when you're dealing with these kind of fuzzy but important concepts.
Okay, so remind me again, what exactly is construct validity? It sounds a bit like a philosophical puzzle.
It's about making sure your measurement aligns with the underlying concept that you're trying to study.
Okay.
So for example, if you're measuring software quality, are you really capturing the essence of quality? Or are you just counting lines of code?
Right, because lines of code might tell you something about the size of the software,
Yeah.
but it doesn't necessarily reflect how well it works or how easy it is to use or how maintainable it is in the long run.
Exactly. And that's where things get tricky, because a lot of the things that we want to measure in software engineering are these kind of abstract concepts. They're not like physical objects that you can put on a scale and weigh.
So how do you measure something that's essentially invisible? It's like trying to measure happiness or creativity.
That's where these statistical measurement models come in.
Okay.
And these models help us to operationalize those concepts by defining them in terms of things that we can measure.
Can you give me a concrete example? I'm a bit of a hands-on learner.
Sure. So let's go back to our bug finding tool example.
Okay.
If we want to measure its impact on software quality,
yeah,
we need to first define what we mean by quality.
Okay.
In this context.
Right.
So maybe we look at the number of bugs that are found after using the tool.
Right.
How long it takes to fix those bugs, or how many bugs reappear later on.
Okay.
And we can combine those individual metrics into a statistical model that gives us a more holistic view of the tool's impact on quality.
Okay.
So it's about breaking down those complex concepts into measurable pieces and then putting them back together.
Okay. That's starting to click. For me, it's like building a puzzle.
Yeah.
Where each piece represents a different aspect of the concept you're trying to measure.
That's a great analogy. And just like with a puzzle, choosing the right pieces and fitting them together correctly is crucial for getting a complete and accurate picture.
Makes sense. Now, you mentioned earlier that different philosophical perspectives can actually influence how we approach measurement.
Yes, they do.
Can you elaborate on that a little bit?
Sure. For instance, positivism emphasizes objective observation and measurement, aiming for quantifiable data.
Yeah.
Whereas realism acknowledges that there might be underlying mechanisms influencing what we observe, even if we can't directly measure them.
So it's about recognizing that different philosophical lenses can lead to different ways of defining and measuring the same concept.
Exactly. And this becomes especially important when you're dealing with what we call multidimensional variables.
Multidimensional variables. Now you're just throwing big words at me.
I'm sorry. It just means that some concepts are made up of multiple interconnected dimensions. Okay. Like, remember, software quality.
Oh, right.
It's not just one thing.
Right.
It's a combination of factors like functionality, reliability, usability, maintainability, and more.
Right. So you can't just measure one aspect of quality and assume you've captured the whole picture.
Exactly. You need a more nuanced approach that considers all of those different dimensions.
Right.
And that's where those statistical models we talked about become even more important.
Okay.
Because they can help us to account for all of those different dimensions and how they relate to each other.
This is making my head spin a little bit, but it's also fascinating to see how much thought and rigor goes into measuring these seemingly simple concepts.
It really does. It's like peeling back the layers of an onion.
Yeah. And when you combine these careful measurement techniques with the right data analysis methods, you can uncover some really valuable insights.
Yes, you can.
Speaking of data analysis, can you remind me of the key methods used in empirical software engineering? We talked about qualitative and quantitative before.
Right.
Are there any others?
Those are the two main categories, but within each, there's a whole toolbox of different techniques.
Okay.
So qualitative methods, remember, are about exploring those why questions.
Right.
Understanding people's experiences and perspectives.
So like conducting interviews or focus groups and then analyzing those transcripts for themes and patterns.
Exactly.
That's what you called thematic analysis, right?
You got it. Now on the quantitative side, it's all about crunching numbers.
Okay.
And testing hypotheses.
So things like running statistical tests to see if there's a relationship between different variables.
Yes.
Like coding style and the number of bugs.
Exactly. And there's a whole range of different statistical techniques.
Wow.
From simple descriptive statistics to more complex inferential statistics that allow us to extract meaning from the data and to draw conclusions.
It's amazing how these different methods can complement each other.
They do.
Allowing researchers to approach a problem from multiple angles.
Yeah.
It's like having a team of investigators, each with their own unique skills and perspectives.
Absolutely. And sometimes the most powerful approach is to combine both qualitative and quantitative methods in what we call a mixed method study.
Okay, that makes sense.
So you get the richness of the qualitative data combined with the rigor of the quantitative data.
You get like a multi-sensory experience of the research problem.
I love that analogy.
So remember MSR, mining software repositories, that technique we were talking about before?
Yeah.
That's actually a key player. It is in empirical software engineering research, and it's worth revisiting in a little bit more detail.
Definitely.
Okay, I'm all ears. I'm fascinated by this idea of being a digital archaeologist digging through the history of a software project.
It's really cool.
It's like having a time machine for software development.
It is. It allows us to extract and analyze all sorts of data from those repositories.
Wow.
We're talking about source code, version control data, bug reports, online forums, even email exchanges between developers.
It's a treasure trove of information about how software is created, maintained, and used.
Exactly. And we can use it to understand how software evolves over time, how developers collaborate, and how different factors impact the quality and maintainability of the code.
Okay.
So, for example, we can analyze commit messages to see how developers describe the changes they're making.
Right.
We can identify patterns in code modifications, and we can even predict potential defects based on past trends.
So it's not just about looking at the code in isolation.
Right.
It's about understanding the entire development process.
Yes.
And the human interactions that shape it.
Exactly. MSR gives us this unique window into the social and technical dynamics of these projects.
That's really cool.
Revealing the hidden connections between people, processes, and products.
This is really making me appreciate the complexity of software development.
Yeah.
It's not just about writing code. It's about navigating this complex web of social and technical interactions.
It really is. And MSR can help us untangle that web and extract valuable insights that can inform how we design, build, and maintain software.
Now, I know we talked about data privacy before, but are there any other ethical considerations that come up with MSR?
Yeah, beyond data privacy, we need to be mindful of how we interpret and communicate our findings.
Okay.
So it's really important to avoid drawing conclusions that aren't supported by the data.
Right.
Or misrepresenting the work of individual developers.
So it's about being responsible researchers, making sure that our work is accurate, fair, and respectful of the people involved.
Exactly. And it's important to remember that the goal of MSR is not to point fingers or to criticize individual developers, but rather to understand those systemic factors that influence software development and to identify opportunities for improvement.
Okay, those are all really important points.
They are.
Now, all of this data analysis and mining sounds pretty technical.
Yeah.
How do you actually teach these concepts in a way that students can grasp?
That's a great question. One of the biggest challenges is helping students to move beyond these abstract concepts and to see how these techniques can be applied to real-world problems.
So less theory, more practice.
Exactly.
Okay.
We need to create learning experiences that are both engaging and relevant.
Okay.
And one way to do that is through these hands-on projects where students can actually analyze open source software repositories. Or work with real-world data sets.
So instead of just reading about MSR in a textbook, they're actually getting their hands dirty and experiencing it firsthand.
Exactly. And it's important to expose them to those tools and technologies that are commonly used in the field.
Okay.
So they can develop those practical skills that they need to succeed.
Makes sense. It's like learning to play a musical instrument.
Yeah.
You can read all the music theory books in the world, but you won't truly master it until you actually pick up the instrument and start playing.
Absolutely. Now, beyond those technical skills.
Yeah.
It's also important to cultivate a critical thinking mindset in students.
Okay.
They need to be able to question assumptions, evaluate evidence, and draw their own conclusions.
So it's not just about following a recipe, it's about being able to think like a researcher and approach problems with a curious and analytical mind.
Exactly. And that's a skill that will serve them well, not just in software engineering, but in any field they choose to pursue.
This has been an incredibly insightful exploration of MSR. Now, before we move on to another fascinating technique, I want to take a step back and talk about the broader context of empirical software engineering research. We've talked about the methods, data analysis, ethical considerations, but what about the underlying philosophies that guide this field?
Yeah, that's a great question, and it might seem like philosophy and software engineering are worlds apart.
Why did you?
But understanding different philosophical perspectives can actually be really helpful in guiding how we design, conduct, and interpret research.
Okay, I'm starting to see the connection.
Yeah.
But can you give me some concrete examples of how philosophy actually influences empirical software engineering?
Sure. Let's start with positivism. Which emphasizes objective observation and measurement. It's all about trying to uncover those universal laws and principles that govern the behavior of software systems.
Oh, wow. So it's like applying the scientific method to software engineering.
Exactly. It's about trying to find those fundamental truths that apply to all software.
Right.
Regardless of the specific context.
So are there universal laws of coding that govern how all software behaves?
That's what the positivists believe.
Wow. Okay, but what about the human side of software development?
Right.
How do we account for the fact that software is created by people,
Yeah.
used by people,
Yeah.
and embedded in this complex social context?
Well, that's where interpretivism comes in.
Okay.
And it recognizes that software isn't just a technical artifact, it's also a social construct that's shaped by human values,
Right.
beliefs, and practices.
So instead of just looking at the code,
Yeah.
we're also considering the human factors involved, like how developers collaborate,
Yeah.
how users interact with the software,
Yeah.
and how cultural norms influence design choices.
You got it.
Okay, that makes a lot of sense, but what if we want to like bridge the gap between these two perspectives?
Okay.
Between the objective world of code and the subjective world of human experience?
Well, that's where critical realism comes in, which attempts to find a middle ground between positivism and interpretivism.
Okay.
And it acknowledges that there are these objective realities out there.
Yeah.
But our understanding of them is always shaped by our social and cultural context.
So it's about being aware of our own biases and assumptions when we're doing research and recognizing that there might be multiple ways of interpreting the same data.
Exactly. And these different philosophical stances can influence everything from the research questions we ask to the data we collect and how we analyze it.
Okay, this is making me think about my own assumptions about software development.
Uh-huh.
I never realized how much my own beliefs and experiences shape the way I approach problems.
That's a great insight.
And it highlights the importance of being aware of our own philosophical leanings and how they might influence our work.
Absolutely.
Okay, so we've got positivism, we've got interpretivism, we've got critical realism.
Yeah.
Are there any other philosophical perspectives that are relevant to empirical software engineering?
Those are some of the main ones.
Okay.
But there are others as well that can be valuable.
Okay.
Like pragmatism, for example.
Yeah.
Which focuses on the practical consequences of our actions and beliefs.
Okay.
Or feminism, which highlights the importance of considering gender and power dynamics in software development.
So it's about recognizing that there are multiple ways of looking at the world, and each perspective can offer valuable insights.
Exactly. And by engaging with those different perspectives, we can really enrich our understanding of software engineering and develop more effective solutions to the challenges that we face.
Now, I know we've talked a lot about the academic side of things, but how do these philosophical ideas actually translate into practice?
Okay.
How can someone who's not a researcher actually benefit from understanding these different perspectives?
That's a great question. And I think one of the biggest benefits is that it can help you to become a more critical thinker.
Okay.
So by understanding different philosophical perspectives, you can start to question assumptions, you can challenge conventional wisdom, and you can approach problems from multiple angles.
So it's about developing a more nuanced and sophisticated way of thinking about software development, rather than just blindly following best practices or accepting things at face value.
Exactly. And that kind of critical thinking is essential in a field like software engineering, where we're constantly dealing with complexity and ambiguity and change.
Okay, I'm convinced. Philosophy might not be about writing code, but it's definitely an important tool for anyone who wants to understand and improve the software development process.
Absolutely. And I think by embracing those different perspectives, we can create a more inclusive and ethical and ultimately more effective software development culture.
This has been an eye-opening discussion about the role of philosophy in empirical software engineering. Now, before we wrap up this episode, I want to touch on another aspect of this field that's incredibly important, and that's teaching.
Okay, teaching is essential. If we want to ensure that the next generation of software engineers is equipped to tackle the challenges of the future, we need to equip them with the skills and knowledge to conduct sound empirical research.
It seems like there's this growing recognition of the need to incorporate empirical methods into software engineering education.
Absolutely. And I think as software systems become more complex and interconnected and data-driven, it's more important than ever for engineers to be able to use data and evidence to make informed decisions.
So it's not just about being able to code, it's also about being able to think critically. analyze data and design experiments.
Absolutely. We need to move beyond that traditional focus on technical skills and cultivate a more holistic understanding of software development that includes these empirical methods.
Now, what are some of the challenges involved in actually teaching empirical software engineering? I imagine it's not always easy to get students excited about research methods and statistics.
You're right. It can be a challenge. One hurdle is that a lot of students come into software engineering programs with a strong background in computer science, but they have very limited exposure to research methods or statistics.
Right. So how do you bridge that gap? How do you make these topics engaging and relevant for students who might be more interested in like building the next killer app?
One approach is to connect those empirical methods to real-world problems that students actually care about. So instead of just presenting these abstract concepts, show them how these methods can be used to improve software quality, enhance user experience, or even to address social issues.
So show them how empirical software engineering can make a real difference in the world.
And hands-on experience is crucial. So instead of just lecturing about research methods, give students opportunities to design and conduct their own research projects. Even if it's on a smaller scale.
So maybe having them analyze open source software repositories. Conduct user studies, experiment with different development techniques.
Exactly. By getting their hands dirty and experiencing that research process firsthand, they're more likely to internalize the concepts and to develop those critical thinking skills that they need to succeed.
That makes a lot of sense. It's about making it real for them. Showing them how these seemingly abstract concepts can be applied to solve practical problems.
Exactly.
Now, what about the future of empirical software engineering education? Do you see any emerging trends or areas of focus?
One trend that I'm really excited about is the growing emphasis on data science. And machine learning in software engineering education.
So maybe incorporating more data science courses into software engineering curricula or developing new courses that specifically focus on applying those techniques to software engineering problems.
Exactly. And we're also seeing a growing focus on human-centered software engineering, which emphasizes the importance of considering the needs and experiences of users throughout the development process.
So making sure that software is not just functional, but also usable. Accessible, enjoyable to use.
Exactly. And empirical methods can play a key role in human-centered software engineering by providing tools and techniques for gathering user feedback, evaluating usability, and designing systems that meet the needs of diverse users.
So maybe incorporating more user research and usability testing into software engineering courses, or even developing new courses that focus on human-centered design principles.
Exactly. And I think these trends are really exciting because they reflect a growing recognition of the importance of empirical methods in shaping the future of software engineering.
This has been an incredibly insightful discussion about the challenges and opportunities of teaching empirical software engineering.
Yeah, it's been fun.
I'm really starting to see how this field is evolving, adapting to the changing landscape of software development.
It is an exciting time to be involved in this field.
It is.
And I think the future holds immense possibilities for those who are equipped with the skills and knowledge to harness its power.
Before we wrap up this deep dive, I want to touch on one final topic that I think brings a lot of these concepts together: simulation.
Simulation, good choice.
Remember when we talked about creating those virtual models of software systems to test different scenarios?
Yes. Simulation is an incredibly powerful tool in empirical software engineering.
It is.
It allows us to experiment with different design choices, to explore the boundaries of a system, and to even predict potential problems before they occur in the real world.
It's like having a digital playground where you can tinker with different variables and see what happens without having to build and deploy the actual software.
Exactly. And that's especially valuable when you're dealing with complex systems where real-world experimentation is just too expensive or too risky or too time-consuming.
So can you give me some concrete examples of how simulation is being used in software engineering research?
Sure. One example is modeling the spread of defects in a code base. So we could use simulation to understand how bugs propagate through the code and to identify potential hotspots where defects are likely to cluster.
So it's like using a computer model to predict where the next earthquake is going to hit, But instead of tectonic plates, we're looking at lines of code.
That's a great analogy.
And we can also use simulation to evaluate the performance of different software architectures.
Yes.
See how they handle different workloads and identify potential bottlenecks.
Absolutely. It's like putting your software architecture through a stress test.
Right.
But instead of physical stress, we're talking about computational stress.
Exactly.
And another really exciting application of simulation is in the field of autonomous systems.
Oh, cool.
We can use simulation to model the behavior of robots and drones in different environments.
Okay.
And to test their navigation algorithms and decision-making processes.
So before you let a self-driving car loose on the streets, you can use simulation to make sure it can handle all sorts of unexpected situations.
Exactly. Simulation allows us to create these virtual worlds where we can experiment with different scenarios and identify potential problems before they cause harm in the real world.
This is all incredibly fascinating, but I have to ask. How do you actually make sure that these simulations are accurate?
Right.
It seems like there's a lot of potential for things to go wrong if your assumptions are off.
You're right.
Or your model just doesn't capture the complexity of the real world.
Creating a valid and reliable simulation is no easy feat.
Right.
It requires a deep understanding of the system you're trying to model.
Okay.
Careful selection of the relevant variables and parameters. And a rigorous testing process. To ensure that the simulation actually behaves as expected.
So it's not just about plugging numbers into a computer program and hoping for the best.
It's not. It's about artfully blending technical expertise with a deep understanding of the real-world context.
Exactly. It's about finding that sweet spot where your simulation is complex enough to capture those essential dynamics of the system, but simple enough to be manageable and interpretable.
Exactly.
Okay, those are all important points, but how do you actually go about building a simulation? Are there any specific tools or techniques that are commonly used in software engineering research?
Yeah, there are a variety of different simulation tools and techniques available.
Okay.
And each has its own strengths and limitations.
Okay.
Some popular tools include discrete event simulation, agent-based modeling, and system dynamics modeling.
Wow.
The choice of tool really depends on the specific research question and the characteristics of the system being modeled.
So it's about choosing the right tool for the job.
Exactly. And it's important to remember that simulation is just one tool in the empirical software engineering toolbox.
Right.
It's not a silver bullet.
Right.
But when used appropriately, it can provide really valuable insights and help us to make better decisions about how we design, build, and maintain software.
This has been an amazing exploration of simulation in software engineering research.
Just a fun topic.
I'm really starting to see the potential of this technique to address these complex problems and to drive innovation.
It's an exciting area with immense possibilities.
It is. All right, before we wrap up this deep dive into empirical software engineering, I want to take a moment to summarize some of the key takeaways and then maybe explore a fascinating case study.
Okay, sounds good.
That brings a lot of these concepts to life.
Great.
So I think one of the big things we talked about was we started by defining empirical software engineering as this use of empirical methods to study and improve software development.
Yeah, you're right.
And we talked about the importance of bridging the gap between research and practice. And how those empirical methods can help us to make more informed decisions about how we build and maintain software.
Exactly. And we also talked about the variety of empirical research methods.
Yes, we did.
Like experiments, surveys, case studies, action research. We talked about the strengths and limitations of each method.
Right. Expert speaker. Even more important because they can help us to account for all those different dimensions and how they all relate to each other.
Right.
This is making my head spin a little bit, but it's also fascinating to see how much thought and rigor goes into measuring these seemingly simple concepts. It's like peeling back the layers of an onion.
It really is. And when you combine these careful measurement techniques with the right data analysis methods, you can uncover some really valuable insights.
Speaking of data analysis, can you remind me of the key methods used in empirical software engineering? We talked about qualitative and quantitative before, but are there any others?
Those are the two main categories, but within each, there's a whole toolbox of different techniques.
Okay.
So qualitative methods, remember, are about exploring those why questions.
Right.
Understanding people's experiences and perspectives.
So like conducting interviews or focus groups. And then analyzing those transcripts for themes and patterns. That's what you called thematic analysis, right?
You got it. Now, on the quantitative side, It's all about crunching numbers.
Okay.
And testing hypotheses.
So things like running statistical tests to see if there's a relationship between different variables like coding style and the number of bugs.
Exactly. And there's a whole range of different statistical techniques, from simple descriptive statistics to more complex inferential statistics that allow us to extract meaning from the data and to draw conclusions.
It's amazing how these different methods can complement each other, allowing researchers to approach a problem from multiple angles.
They do.
It's like having a team of investigators, each with their own unique skills and perspectives.
Absolutely. And sometimes the most powerful approach is to combine both qualitative and quantitative methods in what we call a mixed method study.
Okay, that makes sense. You get the richness of the qualitative data combined with the rigor of the quantitative data. It's like having a multisensory experience of the research problem.
I love that analogy. So remember MSR, mining software repositories.
Yeah.
That technique we were talking about before.
Yeah.
That's actually a key player in empirical software engineering research. And it's worth revisiting in a little bit more detail.
Okay, I'm all ears. I'm fascinated by this idea of being a digital archaeologist digging through the history of a software project. It's like having a time machine for software development.
It is. It allows us to extract and analyze all sorts of data from those repositories.
Wow.
We're talking about source code, version control data, bug reports, online forums, even email exchanges between developers.
Like a treasure trove of information about how software is created, maintained, and used.
Exactly. And we can use it to understand how software evolves over time, how developers collaborate, and how different factors impact the quality and maintainability of the code.
Okay.
So, for example, we can analyze commit messages to see how developers describe the changes they're making.
Right.
We can identify patterns in code modifications, and we can even predict potential defects based on past trends.
So it's not just about looking at the code in isolation, it's about understanding the entire development process and the human interactions that shape it.
Exactly. MSR gives us this unique window into the social and technical dynamics of these projects.
That's really cool.
Revealing the hidden connections between people, processes, and products.
This is really making me appreciate the complexity of software development.
Yeah.
It's not just about writing code, it's about navigating this complex web of social and technical interactions.
It really is, and MSR can help us to untangle that web and extract valuable insights that can inform how we design, build, and maintain software.
Now, I know we talked about data privacy before, but are there any other ethical considerations that come up with MSR?
Yeah, beyond data privacy, we need to be mindful of how we interpret and communicate our findings.
Okay.
So it's really important to avoid drawing conclusions that aren't supported by the data or misrepresenting the work of individual developers.
So it's about being responsible researchers, making sure that our work is accurate, fair, and respectful of the people involved.
Exactly. And it's important to remember that the goal of MSR is not to point fingers or to criticize individual developers, but rather to understand those systemic factors that influence software development and to identify opportunities for improvement.
Okay, those are all really important points.
They are.
Now, all of this data analysis and mining sounds pretty technical. How do you actually teach these concepts in a way that students can grasp?
That's a great question. One of the biggest challenges is helping students to move beyond these abstract concepts and to see how these techniques can be applied to real-world problems.
So less theory, more practice.
Exactly. We need to create learning experiences that are both engaging and relevant.
Okay.
And one way to do that is through these hands-on projects where students can actually analyze open source software repositories or work with real-world data sets.
So instead of just reading about MSR in a textbook, they're actually getting their hands dirty and experiencing it firsthand. Okay.
Yeah, exactly. And it's important to expose them to those tools and technologies that are commonly used in the field so they can develop those practical skills that they need to succeed.
Makes sense. It's like learning to play a musical instrument.
Yeah.
You can read all the music theory books in the world, but you won't truly master it until you'd actually pick up the instrument and start playing.
Absolutely. Now, beyond those technical skills, it's also important to cultivate a critical thinking mindset in students.
Okay.
They need to be able to question assumptions, evaluate evidence, and draw their own conclusions.
So it's not just about following a recipe, it's about being able to think like a researcher and approach problems with a curious and analytical mind.
Exactly. And that's a skill that will serve them well, not just in software engineering, but in any field they choose to pursue.
This has been an incredibly insightful exploration of MSR. But, as we wrap up this whole deep dive into empirical software engineering, I'm walking away with a much deeper appreciation for how much this field has to offer.
I agree.
It's not just about crunching numbers or running experiments. It's about asking the right questions, using the right tools, and always keeping in mind the human element of software development.
It's about using data to tell stories, to uncover insights, and ultimately to create better software for everyone.
And I have a feeling this is just the beginning of a much longer conversation about empirical software engineering.
I think so too. This field is constantly evolving, and there's always something new to learn and explore.
So to all our listeners out there, if you're curious about empirical software engineering, don't be afraid to dive in.
There are tons of resources available, like the handbook we mentioned, and there's a vibrant community of researchers and practitioners who are always happy to share their knowledge and experiences.
So keep exploring, keep questioning, and keep using data to make the world of software a better place. Thanks for joining us.